Okay, so let's start again. Exponential curves. You've already started with exponential curves being y equals, a base to a power of x. So y equals 2 to the power of x, or a to the x, or 5 to the x, or if you want to use the letter e for exponentials, e to the x. So those have usually been your equations. Your condition on a, the bottom base, has been that they've usually been constants, not variables. So that means you haven't had like x to the x. That's a bit too complicated to sketch. Your domain, well, you guys already know how an exponential looks like, right? There it is, cuts at 1. So your domain is all real x, all the x values work. So all real. Your range is everything greater than 0. Y is greater than 0. When x equals 0, you get, for any function, you'll get 2 to the power of 0, let's say. And 2 to the power of 0 is 1, and that's why you get y equals to 1 here. When x is 1, you'll obviously get your base, so you'll get like 2 or a or 5. I don't know, it just makes sense. You're just subbing in. What happens to the limit as x approaches infinity for this function? So what's happening as the x values are approaching infinity? What's happening to the y values? They're increasing as well, right? So the y value would be approaching infinity. And what happens to exponentials as the x value approaches negative infinity? So it'll look like this. Whereas this was like obviously looking like it's 2 to the power of infinity. What's happening as x approaches negative infinity? What's happening to your y value now? Approaching 0, right? Anybody not understand what I've just done there? It's really important to get that. Inverse of a exponential is obviously a log x. We understand that. It's good to always show 2 points on the curve. The reason why we say that is because if you had to draw this one here, compared to this one here, compared to this one here, all 3 will cut through 1, and all 3 will look exactly the same. So it's important for us to see that when you're subbing in numbers, like if I had to sub in 1, you know that the y value of let's say this curve, it's at 2. Or if it was this curve, 5 to the power of 1, it would be at 5. If it was this curve, it would be at e, and so on. All right. So the idea is usually we're going to sketch 2 points, and then that usually will tell us our y values, and if we've obviously drawn our graph right. Okay. Your exponential should be easy because, like I said, it is exactly what you've already done in term 1. So there's nothing really new to learn here, but we just revisit it. So y equals 3 to the x. You can sub in x equals 0. So for exponentials, you can sub in x equals 0. You can find your y-intercept, in other words. So when you go obviously 3 to the 0, you get 1. You know that there's an asymptote here. Don't forget that asymptote. And then of course, let's say sub in our points. So if x equals to 1, you get y equals to 3 to the power of 1, which is 3. When x equals to negative 1, you get y equals to 3 to the power of negative 1, which is obviously a third. So when x is negative 1, it's a third. So let's say there. And obviously when it's 1, it's at 3, which is somewhere there. Now you kind of know the shape, don't you, right? It's just your normal one. There it is. I mean, we like to see these points, like I said, because when you're trying to draw this one and this one, they'll look exactly the same, but at least this one you'll know it's going to be 10 here, and it'll be 1 on 10 here. But anyways, we'll get to that. All right, any questions? Domain, understand that, all real x, range is still greater than 0. Okay, there's no questions. Number 2, y equals 3 to the negative x. How would I draw that? Anyone have any idea of what the negative would do to the x? I think Novak, you should know. You were just working on this yesterday.
Wouldn't
Negative.
it flip it?
Flip how?
Is it
Down or sideways?
uh sideways?
Correct.
Yeah.
Down would be this one. Negative 3 to the x. That means the whole thing's subtracted and it's going to come down. This negative x means all the positive x values become negative, and all your negative x values would become positive because it's a negative x. So a negative x is a flip about the y-axis. So it'll look like this. Really bad drawing, but you guys get the idea. And then all I would do is sub in x equals 1 and negative 1 again, just to check if it's right. If I sub in x equals 1, well, you're going to get y equals to 3 to the negative 1, which is a third. And then when you sub in x equals negative 1, you'll actually get 3. And if you plot that in, there's 1, there's a third, there's negative 1, and there's 3. So if you hadn't assumed it was this way and you had assumed, like, let's just say it was downwards, right? You would have subbed in some numbers and gone, wait, what? What is happening? How come it's above here? And then hopefully you remember, oh yeah, that's not negative the whole thing. So it's not this one. You see it's negative 2. Yeah, that one's you're going to flip down. But this one, no. All right.
Sam, so why do you sub in 1 and -1 again?
So all I'm doing is just literally subbing in 1 into x.
Yeah, but
So
why?
say it again, but
But
why?
why? Like why 1 and -1?
Oh, no reason. I just think one, you've got a number that's in the positive direction. You've already subbed in 0, and then you can sub in -1, which is a number in the negative direction,
Oh, okay.
right? Generally, what you get taught, like back in year 9, year 10, you would have got taught here. Here's a table of value, and then generally you would do -2 all the way to 2. So that way you've got 0, you've got some positives, and you've got some negatives. Now, we don't need all 5. I'm just picking out -1, 0, and 1, just so that you guys can know, oh yeah, when it's at -1, it's somewhere up here. At 1, it's somewhere down there. At 0, it's there. And I know the curve pretty much. I know what's happening. Obviously, as you guys get stronger and stronger with this, the assumption is by the time you guys are in year 12, you wouldn't need to obviously draw any more points. You pretty much look at it and you should know what it's doing. So it's just for now. I've got to show this so you guys don't come back and go, oh, I did a silly mistake. Oh, I got one thing wrong. I drew it the other way around. And I'll just be like, but why didn't you just check it? So it's really important to get used to this as a fail-safe method. Not required, just fail-safe. Any other questions? Okay, y equals 10 to the x. Well, again, I pretty much know the graph of this. Hasn't moved anywhere, hasn't shifted up or down, hasn't shifted left and right. Nothing's really happening. At 10, when I sub in x equals 0, you get 10 to the 0, which is still 1. When I sub in 1, I get 10. When I sub in -1, I get 1 on 10. And then I pretty much already know, because I know it hasn't moved anyways, that that's just going to be a normal exponential. And then there is your asymptote. And obviously you guys can tell what the difference between 10 to the x is compared to 3 to the x. At the same 1 value, 1, 1, this one shoots up a lot faster because he's got to reach to 10. Whereas this guy is going to go only to 3. So all these numbers do in front, it just makes it go a lot faster or a lot steeper. And that's the same thing with your parabolas, if you remember doing that. The 2 in front of x squared doesn't do nothing other than make it steeper. You can't really draw that by hand. Unless you were to draw both of these on the same line, then obviously you have to draw this one a lot steeper than this one. You're not going to draw them on top of each other, of course. All right, any questions? Okay, and we'll go again. X, all right, think about this real quick. And then And then tell me, are there any movements? Has this been shifted up and down, left and right? Is this attached to it? It doesn't look like it. There's no numbers here that are attached to this either. So who thinks they know what this would look like? Any ideas?
It would be wider.
Yeah. Say it again.
It would be wider.
And then you would think it looks like this one, right? This first one. Or
no, wider.
But as in, does it start from the left and go to the yeah, and that's the problem that I'm trying to make sure we don't make mistakes. So that one it looks as innocent as that one does, right? It just looks like, oh, okay, Sam, instead of 10, which was, you said, sharper, 1 on 6 looks like it's wider because that's what we learnt in parabolas. So this would be a lot wider in shape. Correct. But the problem is, if I was to expand this 1 on 6 to the x, I get this, which I know becomes 6 to the power of negative x. All right, so it's actually not the way you were saying it. It's actually steeper, but just starting from the right-hand side and going to the left-hand side. Now, I'm worried you might not see that in an exam, and that's okay. That's no dramas, right? What I've been saying is sub in your points. X equals 0. You're like, oh yeah, anything to the power of 0 is 1. Sweet, there it is. When I sub in 1 on 6 to the power of 1, you're like, wait, what? It's a 6. That's strange. It's down here. Okay, wait. What about if I sub in negative 1? If you had to sub in negative 1 into your calculator, this would have given you 6. So you're like, what is happening? So somehow it's this way, and then you would have observed it a little bit more, and maybe you would have come up with these lines. And that's why I'm teaching it like that right now. You see that, Novak, as well? You were asking it, and there it is. Yeah. That's why we want to sub it in. So it's just to make sure, to guarantee. But I proved it, and yeah, now that I think that was you that was saying it, 1 on 6, usually you're right, it would be wider. But unfortunately, what happens because of these index laws, it actually gets you to 6 to the negative x, which is actually a flip about the y-axis, and then it's still faster than your normal exponentials. Okay, interesting. Let's do another one. 5. Y equals 2 to the x minus 1. Okay, what happens this time when I'm trying to find my, y-intercept? So what happens when I sub in x equals 0? Well, you'll get y equals 2 to the power of 0, take away 1. Okay, so which is a half, right? Or negative 1 is a half. So now you know, hey, this has been moved a little bit actually. It's at a half now. All right, what happens at x equals to 1? X equals to 1, 1 take away 1 is 0. 2 to the power of 0 is 1. So at 1, it's still at 1. So you're like, okay, probably going to be doing this now. But don't rush it. Negative 1. When x equals negative 1, you get y equals 2 to the power of negative 1 minus 1 is negative 2, which is a quarter. And I think our assumption was pretty much right. So there, and there's been no movements up and down, so your asymptote stays the same. It's really important that you understand only this and this will change your asymptotes, up and down. Cool. Left and right, which is what this guy is doing, will not change your asymptotes for exponentials. One more time. Up and down only will affect your exponentials. Left and right, which is what this one's doing, right, because it's attached to the x, will not affect your asymptotes. And that would be the opposite for logs. When we do logs, Obviously, left and right will affect your asymptotes. Up and down won't affect your asymptotes. Because logs and exponentials are opposites of each other. So whatever you learn for one, to learn the other one will be exactly the opposite. All right. Any questions for this one? Okay. Y equals 2 to the x minus 1, and we might as well write this one down. Right? Y equals, all right, perfect. So y equals 2 to the x minus 1. Okay. Obviously, I've hinted enough for you guys to tell you what's happening here. Does someone want to take a guess of what should happen? 2 to the x, take away 1.
Oh, it shifts down 1 unit.
So what do you know?
The asymptote's now at -1.
Your asymptote now is at -1. I agree. Usually it was cutting at 1. Where would it cut now?
Half? No, it's still at 1.
No.
0.
That's interesting. 0.
Yeah.
Why did I 0?
I just checked it on my calculator.
Okay, but other than checking on your calculator, I like what you did. Just quickly, let me just show you what you did so everybody understands. You just went and did, obviously, x equals 0, and you found the y-intercept, right? So you did y equals 2 to the power of 0, which is 1. 1 minus 1 is 0. And you realize it's at 0. But why did I know it was 0 without even substituting it in?
It's because 2 to the power of 0 is 1.
You're still doing it. No, I'm not doing it algebraically.
Oh, okay.
1 minus 1
again?
equals 0.
1 minus 1. Yeah, I think you're pretty much saying it right. So you're saying the original one. And no, it was going through 1, wasn't it? And didn't you say bring everything down 1?
Oh,
So
yeah.
you brought your asymptote down 1. What about your actual curve? Your curve was up here. What's got to happen to your curve?
Oh, it's got to follow it.
It's got to follow. It's got to come down 1 as well. So all your y values, like here, 1, it's going to come down to 0. All right, good work. Makes sense? And again, I mean, you obviously have your fail-safe method. Sub in x equals 0, sub in x equals -1. If you subbed in -1, you would realize, yep, that's a half. Half take away 1 would have given you -half. You're like, what? At -1, it's a negative now? It's down here. And then you would have subbed in 1, and you would have got 1, 2 to the power of 1, take away 1. And then, you would have connected them, and then hopefully you would have remembered, oh yeah, of course, -1 means bring my asymptote down 1. Okay. Last one. That's pretty much as hard as you'll get in advanced, this one here. So there's a lot of different, what can I say? A lot of different transformations that have occurred. Who wants to try what the first step should be? So I'll draw this one, which is y equals 2 to the x. Now what do you got to do to that to start getting it into eventually this? What's your next step to draw? Instead of 2 to the x, what do you want to draw?
2 to the minus x.
Correct. So what do you do?
So you flip out across the x.
There you go. Now you've got 2 to the -x. Then what do you do?
Flip it across the y.
Now you've got -2 to -x, and your asymptote's still at 0.
But then you plus 1.
And then you shift everything up 1. Great work. So instead of it being at -1, it is now cutting at 0. Instead of your asymptote being at 0, it is now an asymptote at 1. Boom. Boom. Done. That wasn't too bad. Look how I drew that. As I gave you a basic one that you're used to. And I said, okay, what does a -x do? Well, you now know the -x flips it about the y-axis. What does a negative do in front of the whole number? Flips it about the x-axis. What does a +1 do? Shifts the whole thing up 1. Great work. So like I said, that's as hard as you get in advanced. Let's look at, before I continue into extension questions, any questions about this? Then we'll do extension 1 graphs. So with extension 1 graphs, there's nothing new to learn. It's just following on everything you've learned from these absolute values of f of x and absolute value of x, and like reciprocal functions and square root functions and y squared equals f of x and absolute value of y equals f of x. So you need to know every single one of these and what their transformations are doing. If you haven't memorized them, I will tell you right now, you should spend the rest of today to memorize exactly what each transformation is doing, because every single topic moving into year 12 will require us to do transformations of this. In fact, there is actually one topic that's literally called translations and dilations via transformations. So you'll be doing an advanced and extension 1 course topic, that requires all of this again. So you might as well learn it from now when you get the time in year 11. Does anyone want me to actually go through the theory of all of these one time? Or do we know every single one? So if I'm saying absolute value of f of x, do you know what's happening there? Compared to absolute value of x, compared to absolute value of y, and then compared to y squared and square root. And
We haven't done these at school, Sam.
You haven't?
Could you go through them?
Yes, absolutely. We have to go through them. Let's do it. So we pause. We pause. Has anyone actually done this at school and hasn't learnt it yet, hasn't memorized it? So like, Emily, have you learnt it at school already?
Yeah, I've learned it at school. I just haven't memorized it.
Cool, cool. Yep. And Nook, you said you haven't done it at school yet?
No, we haven't done it.
Okay. And anyone else?
I've learnt it.
Learnt it and memorized?
Yeah.
Give or take? Okay, cool. Novak, I know you've done it as well. Anybody else? Control with touch. What are we trying to do? We're trying to insert. I need a page. I never inserted a page here actually, but you know what I meant to do? We go view, normal view, and then just go here. And I should be able to write on that, right? All right. So this is how I would do this. This is how I teach, and this is how I would have taught you guys. This particular topic of transformation comes from the Extension 2 course. So the way I do it, I guess it's a very quick method because of the fact that it's an Extension 2 method, and at the same time it's a bit more efficient than trying to go through all the steps that your teachers have been going through and what your textbooks will go through. And that's probably why, let's say, Emily, you've done it but haven't memorized it. So the way I want you to memorize this particular section of Extension 1, graphs, is to know a basic function. There it is, right? You have to memorize that this is going to be a basic function. We're going to transform everything according to this function. And what you want to memorize is this function and its transformation. And once you memorize this function and the transformation, you will apply what you're doing to this function to every other question you'll get. All right. So you're going to memorize this function. I know the other class, they've pretty much, I know some students have taken photos and sent it to me. They've drawn this up onto A4 pieces of paper and then they've just stuck it on their wall, and that's it. They're going to keep it there for the rest of the year. So do the same thing because it's got to be memorized. That's pretty much it. So let's exactly do it the way I would have done it for those guys, which would be breaking it up into little sections. The first one we've got is absolute value of f of x. Okay, so this is a function, and if you ever have absolute value of the whole function, the idea is all negative y values reflect up. all negative y values reflect up. Okay, well, what would that look like? All these negative y values are going to reflect up. Everything else stays the same. There it is. So if you can memorize, this is what I was trying to say. You memorize this, becomes this for that, then that way you'll remember, oh yeah, you don't really need to memorize the words, because once you memorize the diagrams, you'll know what's happened there. You'll know, oh yeah, the negative just flipped up. So if I gave you any other question, if I gave you a question like this, I said, all right, now the absolute value it, you'll just be like, oh yeah, I get it. So Sam said that bit there, that comes up, and then this bit here will reflect up, and then something like that. So pretty much all you need to memorize is more the diagrams. It's a lot easier sometimes than the words. But there you go. So absolute value of the whole thing, that's what's happening. If I had absolute value of the x, just the x, not the whole f of x, just the x, all, see how this says all negative y values reflect up? This is all positive x values reflect left, reflect to the left, or about the y-axis, however you're going to think of it. So all the positive x values, all positive x values are this way, right? Everything from 0 and onwards. There it is. All of these ones will reflect to the left. So this one here, again, it's easier. I've seen it because of my extension 2 kids. It's super easy to memorize these graphs more than all positive x values reflect to the left. All negative y values reflect up. It's a lot harder to know the words. So memorize your graphs for each function. Memorize the function itself, the original function, and then when you see this, you'll know what you've done. You'll be like, oh, what did I do here? Oh yeah, I've taken all the positive x's and it looks like I've just reflected it to the left. So then again, if I give you a different question, if I give you an exponential, and I say, now just do 2 to the absolute value of x, you're like, all right, well, all positive x's, get rid of this. So that's my positive x. Oh yeah, reflect it. Oops. So look almost like a parabola. All right, get rid of that. We'll go again. Y equals, oh, that's the absolute value of y. Absolute value of y equals f of x. So now it's not the right hand side that's absolute valued, it's the left hand side that's absolute valued. This is all positive y values reflect down. So this guy and this guy is pretty much very similar. This was x's absolute value, this was the y's that are absolute value. So all positive y values reflect down. So where's your positive y values? There and there. There and there. Reflect down. Reflect down. That was more meant to go like that. Emily, making sense so far?
Yeah, it is.
And Nook, what about you?
Yeah, it's making sense.
So memorize the diagrams more than the words, I believe. But it's going to come down to you. Like I said, with the other class and every other class I've ever had over the years has always drawn these up and literally memorized the graphs. From the graphs themselves, you'll be able to memorize what is happening. So again, if you were to look at this yourself and you've memorized this graph, you know what it's done to the original. Like, oh yeah, all the positive y values, I've just reflected them down. So it's easy to memorize your graphs than to memorize some of the words. Okay, then we have what? We've got y equals, and then we've got y squared. So y squared is from the same family as absolute values of y, because absolute values of y is positive, y squared is always positive as well. So it's going to be a similar concept to this one here. And just so you know, y squared is the same as plus minus square root f of x. So if you ever have square root questions, they're the same as y squared. So like I said, these two come from the same family. That's how we memorize them. If they come from the same family, then pretty much it's going to be all positive y values reflect down. And that is true. It is all positive y values reflect down. So the only problem is because you've got y squared, what happens is this actually changes concavity and becomes more parabolic in nature. So it doesn't exactly look like this. It's not a straight reflection. It's not this way. It's the other way. It's the other way. It becomes more parabolic in nature, as you can see. You can see it's becoming more parabolas. And another way to think about that, why it's happening, if I pick a number there, let's just say that was 9, you're going to square root that 9 now. So it's going to become 3. And that's why it looks more like these. They're slower, in other words. These are going a lot faster. They're going to shoot up. But same family. So you think of it as, first I've got to do all positive y values reflect down. It's just that instead of a reflection down directly, it is more parabolic in nature. So it's still a reflection down, but it's parabolic instead of a straight reflection. And then if you just had square root, then it's obviously just the top. If you had negative square root, then it's just the bottom. And obviously if it's plus and minus, it's both top and bottom, or if it's y squared, it's both top and bottom. So the top would just be square root f of x, the bottom would be just negative root f of x, and then the whole thing is here. So you don't need to learn two of them. I know they teach you two different graphs here, but they're not, they're the same graph. Cool. So square root f of x and y squared are exactly the same graph. And last one. One on f of x. Okay. This has two things you've got to do. First, all intercepts, x-intercepts become asymptotes. Intercepts become asymptotes. Why does that happen? Think about it. What's the y value here and here? What's the y value? Y equals 0. Right? And if you're going to do 1 over 0, it's going to become undefined. So 1 over any function, wherever, I don't know why I drew it there, wherever the intercepts are, which is right there and there, you've got asymptotes.
And then, so is it just the x-intercepts that become asymptotes?
Yes, just x-intercepts. And then if they're happy, 1 over happy would be a sad, but I'll prove that in a second. So let's look at it with these ones up here. So we're going to look at the numbers on this right hand side. What's 1? Oh, I might draw it up here first. Okay, that's not the answer. That's just this graph. I'm just drawing it here just to show you what's happening. What is 1 over a very small y value? And look, what's 1 over a very small y value?
It's a very large number. It's a larger number.
Very large. And what's 1 over a very large number?
It's a very small number.
Pretty much you'll start to learn when you got these ones, they become like almost hyperbolas. So that becomes like that. This side here, same thing. 1 over small becomes large, 1 over large becomes small. And then that would be your graph for 1 on f of x. And same thing here. 1 over a small number, negative small number, will be a negative large number all the way down here. There it is. And then 1 over a very small becomes very large as well, negative. And then 1 over a larger negative becomes a smaller negative. And that's why you guys can probably see it's starting to do this. So step 1, intercepts and asymptotes. Step 2, 1 over small, large. 1 over large, small. That's all you've got to remember. It's really that simple. Don't need much more than that. Memorize all 5 of these, or all 6, including the original. Memorize the graphs, what it's doing, then you can apply it every single question, no matter what you get. All right. Emily, better?
Yeah, it's good.
All right, let's have a look. Normal, let's go back to this question. Where are we? Normal view. Let's go back to these now. And then if I need to, I'll refer back to that. So look, y equals 2 absolute value of x. Well, that's not this one here. It's not the whole thing that's absolute value. It's just the x that's absolute value. So the x being absolute value is this one here, which says all positive x values will get reflected to the left. Right? So because I've memorized that, I know this is the same as this. So I'm like, okay, well, the original exponential is this. And then, of course, the answer that we're looking for is this. That is y equals, that is super bright. 2 to the x, there you go. Y equals 2 to the x. All positive x values get reflected to the left. Easy. Easy extension 1 question. Not even hard. Once you've memorized these, of course. Anouk, all good as well? Makes sense?
Yeah, all good.
Yeah. So that's pretty much the hardest bit. Memorizing this, and then easy. I'll even send this to you guys. I'll make sure to save it, and I'll graph transformations. Extension. And I'll send it to you guys so you guys can keep that if you want to. What? What happened? Oh, get out of here, Jochen. Alright, I'm back. Don't know what just happened. But anyways, y equals 2 to the x. Alright, let's go another one. Alright, these ones here, these are just addition of ordinates. So you just got to add 2 to the x with 2 to the negative x. So if you've got your original one, which is there, then you've got to have 2 to the negative x, which is there, and then 2 to the x plus 2 to the negative x is just the addition of both of these numbers. So here, 1 plus 1 would get you 2. This number plus another number would be a little bit higher. This number plus close to 0 will be a little bit higher than this number. Really large number, like let's just say 1,000,000 plus almost 0 will be almost 1,000,000. Same thing here. Y value plus another y value will be a little bit higher, a little bit higher, a little bit higher. And pretty much all you'll get is something like this. So it's almost parabolic again. Does that make sense? So what you did, you draw 2x, you draw 2 to the negative x, and then you just add your y values.
Sam, we haven't learnt this at school either.
Yeah, you haven't done addition of ordinates. I get that. 2 to the x plus 2 to the negative x. All you're doing, you're just adding your y values. So this plus this gets you a little bit higher. This plus this, a little bit higher. This one, not as important. Very limited in questions for year 12, if any, really. You don't really do this because, as you guys can see, it's more of an estimation than it is an exact. You're just guessing. So we don't really like this method. especially once you involve calculus. All right, anyways, let's do this. So logs now. Log graphs. So the equation is log x. Well, first, let's draw it up. So this one here, you can tell the asymptote is at x equals 0. All right, and then you can't have any x values that are 0 or negative. So your domain is x is greater than 0, but your range is all real y. And that is the exact opposite of your exponentials. Right, with your exponentials, what did you say? You would have said domain is all real x and your range is y is greater than 0. This one, exact opposite. So your domain becomes x is greater than 0 and your range becomes all real y. Here you had y-intercepts. Cool. Here you won't have any y-intercepts because obviously you can't have x equals 0. Instead, this one's all about y equals to 0. So you'll find your x-intercept. Opposite for logs. So don't think about making x equals 0. Most times won't work. You'll know when x can equal to 0 because it'll be a shift to the left. And that could work. Otherwise, most questions won't. When x equals to 1, well, your equation is log x. When x equals to 1, you get log of 1. Log of 1 is 0. So when x equals to 1, you'll get y equal to 0. So your x-intercept is at 1 when y equals to 0. When x equals to a, you would get log a. What's happening as x is approaching infinity? What's happening to the y value as x approaches infinity? Your y value is also approaching infinity. And then what's happening to your to your y value as your x value is approaching 0 from the positive side? So as x is approaching 0, your y is approaching negative infinity. Can you see that? How this curve here is just going to keep going down to negative infinity. Obviously, the inverse of it is an exponential. All right. All you need to know, anyways, for now is there's your asymptote. If you're going to go left and right, your asymptote will change. If you go up and down, your asymptote won't change. Okay, so opposite of your exponentials. Here you probably won't need x. Okay. All right. Let's look at this. Question 1. f of x equals log 2x sub base 10. What we learned last week is we could rewrite these as ln 2x on ln 10. So dividing by log 10 is just like you saying, okay, Sam, I have this, draw me that compared to draw me this. So it doesn't really do much, or even if you divide by log 10, it doesn't really do much. Log 10 is just a constant. It'll do what you guys were saying before, which is it'll make it wider, But otherwise, it won't do anything else in terms of movements or asymptotes or anything like that. So I've got this graph, and I'm like, okay, I know that this hasn't shifted left or right, so x can still not equal to 0. Because if it did, 2 times 0 is 0, log of 0 is undefined. So I know it can't, I mean, I've got an asymptote there. I already know that. And then I'm like, all right, well, is it cutting at 1? Is it cutting at 2? I'm not too sure. But what I know is I can work out my x-intercept by letting the y value equal to 0. This time, right? You let your y equal to 0. If you thought of letting x equal to 0, you'll come up with the same problem I was just saying. Log of 0 is undefined. So you'll just get math error if you try x equals 0. So 0, you're trying to solve for x. You get rid of log 10 to this side by multiplying it. 0 times log 10 is just 0. We're at this stage. Now I want to solve for x. Any ideas of what I've got to do to both sides? 0 equals log of 2x. What must I do to both sides?
Log them.
It is logged.
Isn't it exponential? So the
Yeah,
a.
yeah, you'll do the opposite of log. So you exponential both sides. E to the 0, anything to the power of 0 is 1. E and log, well, the whole point of why you exponential is so that it can cancel out. So E and log will cancel out. And you're left with 2x, and voila. X equals to a half. And you just draw your log. So a little bit more steps here. So obviously, you're just doing equations again. So if you want to get really strong at your equations, you might as well do log graphs, because you're going to do really well with your graphs as well as your equations at the same time. All right, any questions? Otherwise, I'm going to start question 2. Okay, so question 2. I've got log x squared 5. So I now know, you start to get faster with it. You're like, all right, bang, bang. You could have brought the 2 down. That's fine. It wouldn't have done much. Or it wouldn't. It doesn't make a difference if you bring it down or not when you're trying to solve for now, so it's not an issue. This is 0. 0 times log 5. I know what's going to happen. Right? It's just going to become 0. Again, what do you do to both sides? You probably exponential it. E to the 0 is 1. Oh, when are you allowed to log only? When this is ln. I mean, when are you allowed to exponential? Ln. It can't have a number in front. So it's got to be monic. Right? And then on the other side, it has to be, if there are logs, then it's also got to be only one log. Or if there's a number, then it's just got to be a single number. Cool. And then obviously x equals plus minus 1. But you can't get, it does say here, x is greater than 0. I thought that would have to give it to you. So x equals to 1. You can't get the negative case. So asymptote, still at 0, because log of 0 squared is undefined. and obviously you guys know this hasn't moved left and right, it's just x squared. So the asymptote still at 0, cutting at 1, and voila. Easy stuff. You got no questions? We'll start the next one. Actually, I might let you guys think about it for 1 second. The only thing I want you to tell me is, what is my asymptote? It's not at 0. It is not at 0. And the problem is, if you want me to tell you how to think about it, is you're not allowed to log 0. So think about what x can't be. So if I can't log 0, what can x not be?
It can't be 2, right?
Why?
Oh, you just take that equation in there and solve it. That's what I did.
You are correct. And then question 3 here. You can't have log of 0. So what your logic will be, okay, well then if I can't have 0, I'm going to solve the inside equal to 0. And then I understand that the critical value now is at x equals to 2. I understand that my whole graph has been shifted 2 units to the right. And then of course you would start solving to make sure you can get your y-intercept, sorry, your x-intercept, and then we should be good. So let's solve. 0 equals, again, you know by time you're going to multiply by log 6, it's just going to disappear, so I'm just not going to write it. What do you do to both sides again? So therefore you're going to get 1 equals 3x, take away 6, plus 6 is 7, so therefore x equals to 7 on 3, which is what, 2 1/3. So somewhere there, and voila. So it's not just a straight shift to the right. The reason why it can't be a straight shift to the right is because of all these sub-bases and everything like that. So this one's a little bit more trickier than just shifting to the right. But your asymptote, yes, it's a straight shift to the right. Your intercepts, not exactly. You got to solve for them. All right, brilliant. Okay then, I won't say anything for question 4. I'll give you about a minute or two. Try to see if you can solve it yourself. Still hold a bunch of math and see if you can get it out. All right. What's my critical value? What's my intercept?
-3/2. Oh, never mind.
Yeah, correct. And can you see what you guys link this to another topic you've learned in term 1, extension 1? What about this one? Remember this? You guys were solving for inequalities. What was your first step? First step would have been your denominator cannot equal to 0, right? Because you can't have 1/0. And you would have found a critical value before obviously doing other stuff. Exactly the same logic. You can't have 0 in the denominator, fair enough, you solved it then to make sure where that is. Well, this is exactly the same thing. You can't log 0, so all the time you're going to make the inside equal to 0 and go, okay, there's my asymptote, or this cannot be -3/2, so it's an asymptote. So hopefully the logic makes sense and you're linking topics. So by the end of year 11, we should have linked all the topics together, especially once we do rates of change. Can't isolate the topics. You're going to make it too hard for your prelims if you want to isolate every topic. Okay, that's that. And then obviously you'll make it equal to 0 to find your x-intercept. ln 2x plus 3 exponential 1 take away 3 is -2, x equals -1. Let me know if that was too fast. We know just from drawing that there is going to be a y-intercept. So I can actually work that out. When x equals 0, 2 times 0 is 0. 0 plus 3 is 3. Hey, I actually get log 3 on log 7. So there is a y-intercept. But we know that because we graphed it and we realize, oh, it cuts through the y-intercept. All good? All right, brilliant. Question 5. What does question 5 look like? Absolute value of x. What do we do? Emily, what do you remember from absolute value of x? Not the whole thing being absolute value.
Isn't it only the x values reflect to the left?
Done. See? Easy. So all positive x values, I can tell you the original one looks like this for this one. So log x10. If you solve it, it'll just look like that. Because it's just a log x. And then all positive x values reflect to the left. Done. -1. That's at 1. Happy days. That's extension 1. That won't be in your advanced. And of course, negative x, if it was just negative x, well, that's not plus and minus like this one here. That's just a negative bit, so it'll look like this. -1. Without me solving, because they're all x's only. So I know they're all going to be at -1s. Easy. Okay. Positive x, like this guy, we sketch it to the right. Negative x, we sketch it to the left. Absolute value, so both positive and negative, you sketch them both, left and right. All right, beautiful. That's it, really. There aren't any more questions in advance other than what I've shown you. Obviously, you'll need to practice a few more, but like, that's the idea of them. I don't get any harder than that. So we'll apply it to our extension 1 graphs now, and we'll see how they work. Log of root x. That's an interesting one, actually. That's been asked a few times, and it confuses some students. How can I show you this one? Because you guys got to remember, there was no function where we did this, f of root x, right? We didn't learn this because this is not the square root of the whole thing. That one we have. That's, that was y squared, but f of root x, just the x being square rooted, we didn't have. So this does not exist. Okay, if that doesn't exist, how do I think about this one? And think about your log laws now.
Would you make it to the power of a half?
Beautiful, and then keep going.
Bring the half down.
Yes, see, there was a problem. Think of calculus, bring it down. Calculus, you have to do the same thing. Log, and then you get log x, log 5. So hopefully you guys don't mind me writing like this. Is that okay, Nook? You understand what I've done there?
Yeah, I get it.
Change of base, and then what's the issue? What's my critical value? So what's my asymptote? What can x not be?
0.
And obviously in the fact that it's square root, you can't even have negatives anyways. Like normally you can't have negatives, but there you go. Even with the square root, you can't have negatives.
Yeah.
0, perfect. And then I want to find my x-intercept, so you'll let
y equals 0.
And then 0 times 2 is 0. 0 times log 5 is 0. So you're just going to get 0 equals to log x, exponential,
yeah.
And then x equals to
1.
Easy, you guys. Come on, how come that's an extension 1 question? You know why? Because of the power of half. That's it. You guys look at that and go, I don't know what to do. I've forgotten. What do I do again? No. Just make it easy. We've learned calculus by now, so you guys know when you see surds, you think of it as in terms of halves. It's a lot easier that way. And then log laws. Bring the half down, and easy. Easy, easy. Let's do it again. This one is exactly the one we just did above. So that one's easy. There it is. That's not even the problem. Okay, this one. Log of negative x and then absolute value of y. All right, anyone remember what we do with absolute value of y? So there's the original one. What did we do for the absolute value of y to this?
You'd bring the bottom, the negative y and values up so it'll look like a
Oh,
W.
good try. Now it's this. The one you're talking about is this.
Oh, yeah.
Absolute value of f of x.
Oh, yeah. Would it
Is
look
it-
like that with sideways thing?
That was y squared.
Oh, okay.
Is it all positive y values reflect down?
Yeah, all positive y values. So this way, it gets reflected down. I think when you said sideways, I think you were talking about more this one here.
Yeah, that's what I was talking about.
Yeah, I thought so. So this one's all positive y's get reflected down. So they look something like this. So pretty much same thing here, but there's a lot of things happening. So the first thing I would draw is log of negative x. Well, again, we've done that. We understand log of negative x is there. And then, of course, absolute value of y, all positive y values reflect down. And that would be your answer for absolute value of y equals log subbase 10. And the reason why I'm not solving, if you guys are thinking, like, how come you're not solving for -1 and whatever, I know it's just x. So it hasn't shifted left or right or anything like that. So I just know it's always going to be at 1. If there was like this one here, I knew it was also going to be at 1, but I decided to do it anyways. But if it's just x on its own, then it's always going to be at 1. And I think that's okay. One more. Y squared. Oh, well, Anouk, what do we do with y squared?
Oh, you square root. It's gonna be that thing.
That one. So pretty much this one and this one will look the same. The only difference between the two is that you see how this one's obviously it's just a straight reflection. When you're doing y squared, these numbers, because I mean, let me show it. If I didn't have the y squared and I had this, what you're doing to each of your y values of your original graph is you're square rooting them. So all of these numbers here are all getting square rooted. So they're getting smaller and smaller. So if you had like, obviously if you had 16, it becomes 4. If you had 81, it becomes 9. If you had, 225, look how large 225 has to be. It's got to be all the way up here. But then square root of that, you're going to get down to 15. And that's why we say they're a bit more parabolic in nature. So same concept, but a little bit more parabolic is what you're aiming for. So maybe even if you want to exaggerate it, there you go. I think you guys get that now. Cool. Any questions? These would be worth about, in your extension 1 exam, well, in extension 2, they were worth 2 marks. So I think in extension 1, they will still be worth 2 marks. So there you go. 2 mark questions. And they were usually worth, in an exam, in extension 2, they were worth about 10 marks. So they gave you about 5 of them. Pretty much the 5 I just gave you, the 5 you need to know. And that was pretty easy, 10 marks in an extension 2 paper. And same thing with extension 1, they're not that hard. Once you know each transformation. Yeah.
Are both those curves part of the graph you just drew?
No. I was just saying if you want to exaggerate it and show it a little bit steeper, you could do that.
Okay.
Only one of the answers. Like me, I would have just drawn the top one.
All right.
But whatever if you want to exaggerate it a little bit more, you could show it like that. All right, I think that's it. We're up to applications. Cool. So last bit, and we're wrapping up logs and exponentials. So you can see the graph bit, it's not really that hard. It's a bit more x and y steps, and then just your transformations that you got to remember. The applications, actually not hard. We're going to obviously apply everything that you now have learned into HSC questions. So every single one here, we're just taken from HSC questions, and that's what you guys got to start learning to do. Every question you do has to be HSC. You can't do just year 11 questions or textbook questions. They're not going to be good enough. Yeah, HSC, every single one. Okay. So if I have to do HSC questions, you've got to do them as well. Move away from your textbook questions. Don't repeat what you just did in term 1. All right. Most questions in this section make use of the exponent e instead of 2, 3s, and 10s. So simply treat e as another one of these numerals for the time being. There'll be a more in-depth study of e later on when we do calculus. So we've already finished calculus, which is why we're going to move on to rates of change in extension 1, which will combine logs and exponentials with calculus. All right, let's start. This was in the 2000 2-unit HSC. Question 9. Question 9 is your second last question of the HSC. Second last question of the HSC means band 6 students, pretty much, 90 plus only. So the students that are under 90 plus should be able to answer and get full marks for this. That's an easy one. Sketch y equals log ex. Log e, I don't think I said this last week, but log e is specifically ln. I did say ln is base e, but I never actually said log e is ln. So just to make it clear, log e is specifically ln. So you don't need to write ln x on ln e, because log e is 1 anyways, but it's just ln x. So sketch y equals ln x, and look how many marks it's worth. 2. Nice and easy. ln x, we know the asymptote's at 0. There's my intercept of 1. Thank you very much. Easy 2 marks. Double I. All right, on the same sketch, find graphically the number of solutions of the equation ln x take away x equals -2. I want to make a quick point of something. You see this question here? You would never see this in the textbook. These are not textbook style questions. These are exam questions. And unless you start to learn to look through exam papers and do exam questions, you won't expose yourself to exam style questions. So you'll jump into your exams and you won't be able to understand what it's saying, because they're worded a little bit differently to your textbook style questions. So as soon as you can, once you're ready, you just move away from these textbooks and start exams. On the same sketch, find graphically the number of solutions of the equation ln x take away x equals -2. All right, does anyone have any ideas what it's trying to at least say? Number of solutions of the equation graphically. Just a guess. I don't want to hear any right or wrong answers. I just want to hear guesses. Say it. It's good to guess things. Tell me anything you're thinking of.
Could you put them as a fraction because it's a minus?
Could you put it? You can't. Good point. Why can't you do that? They're not both.
Oh, yeah, they're not. Yeah, okay.
They're not both logs.
Yeah.
No, cannot. On the same sketch. So it's trying to say, obviously sketch something else. So what's the other thing you're meant to sketch? It's obviously in front of you, but you guys got to think about how it's going to work. So come on, give me some things you're saying.
Sam,
Yeah,
it says y equals log ex.
correct.
So can you change y for log ex or not?
Yes. Fantastic. You're the first one this week that's at least said something like that. All right, fair enough. Yes, and then?
And then make y equals x minus 2.
You found it. Done. He said it. Great. Great. See? You thought, oh, can you do this? Or can... It's okay. You've got to learn to try. Because if you don't try, you won't know what would happen. Absolutely. Y, take away x. You said log x is just y. Change it for y. Minus x equals -2, and then just plus it over. You found your second equation. Y equals x take away 2. So, draw this. X equals 0. Y equals -2. When y equals 0, x equals 2. There's this. See, on the same sketch, find graphically the number of solutions. What's going to eventually happen to these two? These two will meet, right? This guy's going to shoot up. This guy's going to plateau a bit. That's what happens with logs. And of course, how many solutions are there? Two solutions. So the drawing bit wasn't too hard. It's more about recognizing what Novak just recognized, that this log x is just another way of saying y. And this equation is there, y equals x take away 2. And the reason why that works, so I mean, this is, you did it a very out of the box way, Novak. Like, it's not something we've done before, but great. So that's why I didn't say nothing. But the way you guys have done it before is you would have usually had y equals log x and another equation, i.e. you would have had this. So this had to move to this side, so that when you solved simultaneously, you would have said, hey, y's and y's are the same, so these two need to be the same. And then, of course, all they've done is brought the x over. And so all you had to do was just bring the x over, and you should have realized, yeah, that's my y value for one equation, that's my y value for the other equation. So that's what they wanted you to see, but Novak, I think you made it even easier. I like that. I might start using that one. So y, ln x equals y, just replace it, and there it is. Simple. Draw it. And if you're wondering how I knew these two are going to meet here and not just like go up like this straight, if you want to try some numbers, try log of like 99. Just do log of 99. Look at the number it will give you. It says 4.59. So at 99, you know, for this graph, for your straight line, it's going to be like 99 or 97 or whatever. But at 99, this one's just going to be at 4. So it's very slow to go up. So this is super slow, so that's why it's going to look more like this. And it'll touch once and twice. And you see that thinking? That's when we're talking about the band 6. The only way you've been able to get to that level is by looking at exam questions. You've understood what to do. You've done this style of thinking before. It's the only way. Textbooks will never help you with this. All right, let's go. At 1990s, 2-unit HSC question 7. Question 7 means band 5, so 80 plus students. So, you know, a lot of students should be able to answer this pretty freely, because it's just basic exponential equations. Don't read into the words too much, but here we go. A quantity Q of radium at time t in years given by Q equals Q naught E negative KT, where K is a constant and Q naught is the initial amount of radium at time t equals 0. Okay, hi. Given that Q equals half of Q naught, given that Q is half Q naught, when time is 1690, calculate the value of K. All right. So what's my first step? They say given that Q is half of Q naught, when T is 1690, what would you guys usually do when you're given this information? Q is half Q naught. T is 1690. What are you thinking? If I was to give you something is something else, T is something else, what would you do?
And
Come on.
just sub it in.
There we go. That's what I want to hear. You got it. Your head's got to say, no, just sub it in, or just use it, put it in somewhere, and that's it. Your Q, this Q becomes half Q0. Half Q0 equals Q0 E negative. Remember, you're trying to solve for K. Negative KT. T is 1690. I'll just rearrange that so it'll look a little bit nicer. There it is. We're trying to solve for K. What's the next thing I would get rid of? Trying to eventually get all the way up to here. So what's stopping you? A lot of things. It's the first thing I will get rid of. And how? You want to get rid of this Q naught, right? So imagine you had a question that said this. You're trying to solve for K, you get rid of the 2 first by dividing it. So exactly the same logic. You would get rid of your Q naught by dividing it, and then disappears, as it should, because you want to solve for K. You're left with a half equals E negative 1690K. Now what do? E, I want to get all the way to K. 1690 stopping me, the negative, and then the E stopping me. So what's my next step?
Would you log it, then bring down 1690?
You are correct. You log both sides. This guy cancels out. These two don't cancel, so that just becomes log of half equals bring down the 1690. And then, what is K equal to? Over 1690. Does that make sense? So just look through those lines and then get an answer. Plug that into your calculator. And literally you guys are going to do it again with 20%. But first get the answer for this one. Log 0.5 over negative 1690. 0.000410. 41. Then we do it again. After how many years does only 20% of the initial amount of radium remain? All right, what letter are you looking for? To ask for after how many years?
We're looking for T, right?
Right, and so 20% of the initial amount. So what does Q equal to?
The amount of radium.
Yeah, so 20% of the initial radium in this case now.
Yeah.
So then it'll be 20%, which is 1 on 5, or 0.2, whatever you guys like to write, equals Q naught E negative K, which you know is this. But who wants to keep writing this out? But anyways, I usually just write it as K, because you know it's a constant. Ugh. And then T. All right, what's your next step? Get rid of Q naught. Log both sides, so it's exactly the same. This guy comes down. And this guy comes down. Negative 0.00041 T. And then how do I find time? T equals log 0.2 over negative 0.00041. Now, quick point about this. It's 3,924 years. Now, you guys got to learn something here. It was obviously said to you a few times, you know, when you're in year 9, year 10, but it gets very important now in year 11 and 12. Here, we rounded. You can write down the answer and you can use, so you can write down here and you can use it for your next questions, the rounded answer, but in your final answer, so right here, you cannot use a rounded answer. It's got to be the exact value. So I didn't put in negative 0.00041. I left it as it was, log 0.5 over negative 1690, whatever that answer was. So the full unrounded answer. You can write it, but you can't use it at the end. At the end, you've got to use the exact answer. So a way to do that, if you don't want to keep rewriting it, don't forget here, you can press Shift STO, which is on top of the number 7 button, right, on top of the 7, Shift Store, and then pick a letter, A, B, C, D, and that will actually store it as those letters. And then all you will do here is do log of 0.2 over, let's say A, which would be alpha, because it's red, alpha A, or alpha B, alpha C. Just keep that in mind. Don't use a rounded answer at the end, because you're going to round twice, that means, and then your last one you could have probably had 3,925 years or 3,923 years, and that would be wrong. Okay. Any questions? If there aren't any questions, do you want to try I for this one? So pretty much the same thing. They gave you the equation, A equals 10E negative KT, and they said calculate K given A is 3.2 and time is 4. So try that. A equals 10, again, 1992 HSC. Question 4. Question 4 means pretty much band 3 now, band 3 to 4. So about 60%. The reason why this is a lot easier than this one here, you have to understand Q is half of Q naught, means replace the Q for half Q naught and then divide the Q. And that's the only reason why it was a little bit more band 5 style, whereas this is really easy. It just says calculate K given that A is 3.2 and T is 4. So the numbers are easy, everything's easy. And that's why it's earlier on. Negative T is 4K. All right, go. Try to see if you can solve for K. Let me know when you've got an answer. Okay. Anybody able to get K out? I know you guys are working on it still, but who wants to try it? Tell me the first step, maybe. Shania, do you want to start me off? 3.2 equals 10 E negative 4K. What's your next line?
Do you divide it by 10?
Yep. So you would get 0.32 equals negative 4k. And what would you do? Now what do you do? You've got the e there that you don't like.
You log both sides.
Then you're left with log of 0.32 equals negative 4k, and you're literally one step away. You just want k. What do you do with the negative 4 now? Divide.
Yep, sorry.
That's right. Divide by negative 4. And you're done. And again, you guys know you're going to use this. That's just how it works when you find k. So what you do when you find an answer, is log 0.32 over negative 4 is 0.282849. But what I do before I get rid of it, I press Shift, Store, and I'm pressing A. So Shift, Store, which is also the RCL button, which is on top of 7. So Shift, Store, and then I pressed on top of the RCL, which is A. Now it's stored as A, but you would write that down, but you don't use that. Just keep that in. Anyone not sure about any steps here? No, we're good. After how many hours does 1 kilogram of sugar remain undissolved? After how many hours does 1 kilogram of sugar remain undissolved? All right, Andy, tell me, what does, obviously, what letter are you solving for?
A.
No, solving for after how many hours?
Oh. T.
T, you're solving for T. What do you have? You've already got A. A is what? In this case now. After how many hours does 1 kilogram sugar remain? What does A stand for?
1.
Yeah, A is undissolved sugar, so A is 1. 10E negative K, you already have K, but instead of writing this down, maybe you want to just leave it as K. It's probably a bit easier. All right, let's do it. What's the first thing you get rid of?
The 10E.
Oh, we can't do 10E, just the 10.
Oh, okay.
So how do I get rid of the 10?
You divide it?
Yeah, exactly what we just did here. Divide it. 1 on 10, which is 0.1. There it is. Now how do I get rid of E?
Log it.
Log of 1 over 10, just write it as log 0.1, it's easier. Log, and this cancels out, your power comes to the bottom. You're trying to solve for T, what do you divide?
K. Negative K.
There you go. Over negative K, which is log 0.1 over negative, 0.289, whatever, 2849. And that's it. Plug it into your calculator, use the exact answer, divided by negative alpha A. 8 point. So after how many hours does 1 kilogram of sugar remain? After 8.08 hours. Doesn't say to the nearest minute, so you can use it as 0.08. So Andy, just be careful. At the beginning you said divide by 10e. The only reason why you can't do that is because it's got a power. If it was if it was actually this, let's say that, and you're solving for x, absolutely, just say divide by 10e and your answer is right. Like, that is the answer for x. But if it was power of x, then no, you can't. You would have to do 1 on 10, and then you have to log both sides, and then your answer is log 1 on 10 equals x. So just, be careful with that. That's fine.
Yeah, okay.
Cool. Done. All right. Anybody else have any questions for us? You've just done 3 HSC questions. Look at that. I'll leave one for you. Question 3 shouldn't be too hard. Question 10, going to be hard. Right, question 10 is not band 6 only, it's 95 plus. And especially when you're going to go down to like 1980. So if you're going to do the 2010s onwards, let's just say it's going to be easy. If you're going to go 2000s onwards, it's going to be medium. You're going to go 1990s onwards, it's going to be hard. Then you go 1980s, it's going to be very hard. If you go to 1970s, it's just going to be gibberish hard. All right, and this is where you want to get to. If you want to get to 99 and 100, you pretty much need to be able to do these styles of questions, the 1970s. So they've obviously gotten a lot easier as the years have gone by, because less and less people are doing good at math, and there's less people that are doing advanced math and extension math, so they're making it even easier and easier as the years have gone by. But for the really hard ones, like the question 10s, you pretty much need to be at this level of knowledge. So these papers are going to be really hard. This is where you want to get to eventually. Right now, you can get to this stage for year 11. Year 12, you get to this stage. Okay, let's have a look at this. Question 10. A population n of t, so this is just like f of x, you guys know, varies with time according to the law n of t is equal to c e k t, where c and k are positive constants and time is greater than 0. Show that if a and b are two positive numbers such that a plus b is equal to 1, then n of at plus bu is equal to n of t to the power of a, n of u to the power of b. For any t is greater than or equal to 0, y is greater than or equal to 0. Okay, again, I'm just going to say, anyone know what it's talking about? N of t is equal to CEKT. Now it says n of AT plus BU. And we want it to become this. Any ideas? What do you see? Talk to me. What do you see?
A plus B equals 1, and if you times those, I
The
mean, if you
re-
plus those.
But why aren't you allowed to actually multiply these? Are they the same basis?
No.
No. So good. You will be using it somehow, absolutely. It's just that you can't because these bases aren't the same. If this was t, yeah, you're right. Like a, nt, it will be a plus b, and a plus b is 1. But no, you can't do that. Bases are not the same. So, good. We will use what you just said soon. It's just not yet because you're not allowed to. Okay, then I'll give you a hint. What about this one and this one? What does it mean? Think of your functions. When you said n of t or f of x, and then
You sub in at plus b.
That's what I like to hear. You see how you can relate topics? If I gave you f of x back in term 1 is this. Then I came up to you and I said, in calculus, we did f of x plus h. What did we do there? We said, hey, replace all your x's for x plus h. Then also in term 1, you did, odds and evens where you replaced them for negative x. Then you did obviously the easy ones where you replaced them for like 2's. F of 2 became 2 squared, whatever, you get the idea. We replaced the letters for the x. In this case, it's saying it's not x, it's actually t. So when you're saying n of at plus bu, whenever it's a show question, you do the left-hand side, So left-hand side is n of at plus bu. Well, n of at plus bu becomes CE C, E, K. Instead of T, it's AT plus BU. Do we get that? Or we going to say that again? C, E, K. Instead of the T, replace it for, or substitute it for AT plus BU. Exactly what it's saying. Okay. Next line, what would you do now? Think of what Shania was saying just before as well. So definitely going to bring some index laws in. And keep an eye on what this means. N of T. NT means exactly that. So that's C, E, K, T. What does N of U mean? What's N of U? Someone tell me the answer for NU.
You need sub in U.
So what's the answer?
CEKU.
KU. Good. Okay. So what would you do with this right now? If you had this in your exam, you got up to this stage, what would be your next line? Me, I would be like, well, I don't like these brackets. I'm just going to expand it, right? That would be me. KAT, and then plus KBU. And then I'm thinking, like, my God, I'm so close. EKU, KU, KT, KT. There's an A, there's an A, there's a B, there's a B. All right, maybe Shania, maybe you might be able to tell us, what do we do? There's an exponential that says KAT plus KBU. Can I somehow break this up? There's a plus sign there. I should be able to break it up. E to the power of what? Multiplied by E to the power of what? Gets me these two. Shania, any ideas?
Oh, I think you move the A and B to one side and the
You can't. You can't because there's no common factor other than K. So you don't want to factorize it and getting into this stage. You're here, you've got a plus sign, and in the indices, you've got a plus sign. So I've broken up my bases as E and E. What would this be? This is E to the power of what multiplied by E to the power of what would get me E to the power of KAT plus KBU.
KTU
Yes.
and then A plus B and B.
No, not exactly. KBU. That. Think about it. What happens when you're multiplying your bases here?
And you plus them, yep.
See? So E to the power of KAT plus KBU is the same as EKAT, EKBU. And then, of course, I think you guys can obviously see that becomes C, E, K, T to the power of A. And that becomes E, K, U, EKU to the power of B, because power to power you just multiply. You're like, but Sam, that's still not C. I agree. If I bring the C in, so therefore you would get C to the power of A, C to the power of Yep. So just have a look at something. So we've got C, if I put it to the power of A, if I just did, and then here I did C to the power of B, what would that be? C to the power of what? If I did C to the power of A times
C.
And then what's A plus B equal to?
1.
So C to the power of A times C to the power of B is equal to C to the power of A plus B, which is C to the power of 1, which is the C that I've got here. So I can break up this C as C to the A times C to the B. That's a tricky one. And I'm only doing that because I'm trying to force this c inside. And then of course now you've got them both as cekt to the power of a multiplied by c. So I kind of forced it. Now that, and you're done, equals n of t. Now that, obviously, I just said is, it's really equals right hand side. So 1 mark, by the time you get into the 95 stage, 1 mark in 95 plus is usually about half a page of working out. And the thinking, as you can see, you've got to be at 100%. Like, you've got to know what you're doing for letters without just instead of just numbers. So our first thing was, yep, we understood that was just a straight substitution. Then when I have exponentials like that, I would expand it. Then I know powers, I've learned if I plus it, it's the same as multiplying. And then the idea is you're trying to get it in terms of A. So I got rid of the A, I put them on the top, B, then I thought of, wait, how the heck am I going to bring this C in? It's really weird. And then I realized, oh, I haven't used this A plus B to the power of 1 yet. So what I'm doing is I think about, okay, well, that's C to the A, and that's C to the B. CA times CB becomes CA plus B, and then I realize, oh, that is just C. So that's just a sneaky one, some sneaky algebra here. And then obviously you're done. The only way, I can't keep emphasizing this, only way you can think like this is by doing exam questions. There is no textbook in the world that will allow you to think like this. That's the only way. As you can see, Norman Hurst's boys, where we teach these notes, of course, that's all we do. That's all we give them. HSC questions. No need for textbooks. No Maths in Focus, no Cambridge, no nothing like that. Just straight HSC exams once we've covered the theory. You guys got to start learning to do the same thing. The only way you can think the way I just thought is by exposing yourself to exams. It's the only thing that will get you there. And it's not, I'm not just biasing this from math. It's absolutely all your subjects. You go economics, the only way you're going to do well is by memorizing the last 10, 15 years of short response questions. You'll realize there's a pattern in the styles of questions they ask. You'll go into your exams, you already know what they're going to say because you've memorized the last 15 questions, but last 15 years of past papers, and they just repeat again and again and again. All right. That was 1 mark. Now for 2 marks. Let's see. Answer otherwise, find N13. Given that N3 is equal to 10 and N18 is equal to 100. All right, any ideas of how we're going to do this? N3 is 10, so N of 3. So you would assume T is what, 3? And if you assumed it was 18, then you would get what, 3A plus 18B. I don't know if that helps much. Find N of 13. N of 13. Let's see. N of T, NT is equal to N of U, N of 18. N of 13. What's the way I would do it? What's the way I would do it? Why would I have not? I wouldn't have used this. All right, so I would have done n of 13 equals CE. T is 13, right? So E 13K. That's what we want to find. Now you know that n of 3 equals C E 3K, and you know n of 18 equals C E 18K, right? We know that n of 3 is equal to 10. We know that n of 18 equals to 100. You can see there's two missing letters, so we're just going to solve simultaneously. So from equation 1, I'll make C the subject, so it'll look like this. C the subject, so it'll look like this. C equals 10 on E 3K. Sub this into here, sub 3 into 2. So it would look like this, 10 on E 3K dot E 18K equals to 100. 18K divided by E 3K, that becomes a takeaway, so 18K takeaway 3K. So what's that, 15K? Divide by 10, and then hopefully this looks familiar. Log both sides. And then divide by 15. We found K, sub it into here, you'll find C. So C equals 10 on E 3K, where K is that. I'll quickly sub that in. 3 times log 10 on 15, exponential that, and then 10 divided by that answer gives me about 6.3. Where are we? 6.3 for C, and then K is log 10 over 15, 0.15. Sub in C and K into here now. So n of 13 equals C, which is 6.3, E 13K. And that's the answer to that one. On 15. So about 46.35 is the answer for N13. So that was a tricky simultaneous equation that you're just not used to, because again, it's an exam style question, so you usually don't get to see simultaneous questions like this with ease. Well, all I did was make C the subject and did substitution. Made E the subject, substituted into here, did a bit of algebra, solved for K. Once I find K, go back up here, sub it into K, find C. Once I found C and K, go back to the original one here, substitute that in, and you're done. Next week, I'll actually probably spend a little bit more time going through some more applications of logs before we start extension 1. So please revise this. Otherwise, it's going to get really hard once we get to the extension 1 sections.